Welcome to Odor Always Moves, where we're translating the complexity of odor movement down to the operational level for canine trainers and handlers. This is the seventh video in the series, and we're going to be talking about the impacts on odor concentration, specifically wind speeds and different barrier types. As always, this is dedicated to my first bomb dog, Daisy. And this is for educational purposes only. It is not intended to be a training video for you or your dog. It's just to help you visualize how odor moves in complex environments. So when we talk concentration, we're not talking about, thinking really hard, getting ready for an exam or something. But to understand odor movement, we do need to comprehend the importance of odor concentration specifically, and what does it mean, and then what influences it, such as the source and the environment. Now, concentration in this context is really just the measure of something, the amount of something relative to the amount of something else in a defined volume. Okay, and so really it's just the percent or the quantity of something relative to a mixture. And for us, we are looking specifically at how much odorous gas there is in relation to the amount of air in that area. That's what we're talking about when we use the word concentration or odor concentration. And we use the analogy of a tennis ball representing the odor. Well, you can see all the white balls; those are ping pong balls, and those represent air. So hopefully this will help you visualize this. Is I have this big volume of ping pong balls, and that's air, but I have one tennis ball in there, one molecule of odor. So let's say I have 1 million ping pong balls and one tennis ball of odor, right? Well, that would be the concentration of the odor would be 1 part per million. One tennis ball relative to 1 million ping pong balls. And so that's often how concentration is measured, and you'll hear those terms. You'll even see these, the letters, ppm or ppb. Yeah, those are parts per million, parts per billion, and oftentimes you'll even see it parts per trillion. Okay, and this can be in relation to the mass. So it could be one gram to 1 million grams, or molecules, one mole or molecules for 1 million molecules or moles. But it can also be in relation to the volume, percent volume specifically, in that it's basically saying my odor is going to take up 1 millionth of the volume that the air is taking up. Okay, and so that's a percent volume. Just so you know, that's actually what my models are looking at, is percent volume. Is so when you're seeing it, it's not a measure of how many molecules are there. It's just relative to that's how much odor, how much volume of the model space is being taken up by that odor at that particular point. Okay. Now, is a no-brainer. High concentration of odor usually is more easily detected by a dog, and I say usually because there are times when you can have too much concentration and in a big area, and it's difficult for the dog to find the source of it because it's kind of overwhelming to it. But that's kind of not the norm. But it's just something to kind of keep in mind that you can have too much concentration, and it can impact a search. So with concentration, size matters. And when I say size, I'm talking about the volume of space where the odor is, actually occurring and being released. And that space relative to the amount of odor can dictate its amount of concentration. So on the left, you can see that we have a kind of a localized, you know, source of odor. So we have 3 tennis balls, and we have this cube of air. And if I take that same cube, but I make it bigger, and so there's more air, but I leave the same amount of odor, well, this area and this odor has a lower concentration than this one, just because the volume, the amount of air has increased. So that's something to kind of keep in mind. And what is important, though, is that the local concentration stays the same. So even though the overall concentration, say the odor in the room, is the same, but the local concentration, where that odor is at, is staying the same. So it's still concentrated. And we've seen that in the models where you'll have localized concentration. And then when we look at percent volume, okay, and let's just say we have the exact same amount of space, the exact same amount of air, and the same amount of odor. The difference is how closely connected those odor molecules are relative to one another. What's their spacing? Okay, so here they're tightly together. This is a high localized concentration. Okay, and this would be representative of maybe at the source. And then, but we have the same amount of space, same amount of air, and now we have the same odor, but it's now spread apart. So that's a lower localized concentration. And so that you see that as it gets further and further away from the source and maybe influenced by air movement, that kind of stuff. And we've seen this before in the prior videos, and specifically the last video on ventilation systems, where the ventilation system is designed to spread air and mix it up. Well, because of that, you can have areas of very high concentration that's well away from the source, and lower and medium levels of concentration, and then basically the entire environment is filled up with low concentration. That's where those tennis balls are spread out further apart. Okay, so that's just something to kind of keep in mind. Now, the key factors that, with regard to odor concentration, and we talked, source environment, is what we're going to talk about the source is how much odorous gas has been released and it continues to be released from the source and its properties. Because if you have a release of gas and it stops, and it's going to spread out, it's going to get diffused, and eventually it'll get to such a low concentration the dog can't detect it. But in our world, we're typically looking for a source that is continually emitting an odor. Okay? And the things that influence that amount that's being released and has been released are, well, first and foremost, is vapor pressure. And really, that's just how excitable the molecules are in that source material. Okay? The more excitable they are, the more gas it wants to release. And then temperature, well, that influences the vapor pressure and how excited those molecules are. The higher the temperature, the more excited they get, they move around faster, and the sublimation rate, which is the release of a gas from a solid, that increases with temperature increase. And then the other thing is really important. A lot of times people emphasize the mass, the weight of something, and really that is not the key thing for sublimation. It's surface area. It's what's exposed to the air. That's what's dictating the release of odor. And so we can control that. There's been some great presentations on that and research. But if you just even look at the equations defining sublimation, mass isn't in there, surface area is. And then the other thing that influences it, this is a containment method. So what's it in? Is it in a glass jar? Is it in a paper bag? Is it spread out over the ground? Okay, all those things matter in terms of how much odor is being released. And then the last thing, and this kind of is getting into the environment side, but we're still going to put it on the source, is molecular diffusion. So we understand that these gas molecules are bouncing off one another. Whether or not the air is moving or not, the molecules are moving, they're bouncing off things, and they're bouncing off each other, they're bouncing off the air molecules, they're bouncing off the objects, and because of that, they spread out naturally. And every gas has a unique diffusion coefficient, and some gases spread out very quickly, and others spread out very slow. Okay, and so absent of the air movement, in advection, which we're going to get into, this influences how far out from the source concentrated levels can reach. And we'll see that in the models because I use odors of different diffusion coefficients just to kind of help visualize that. So now let's take a look at the environment and how that impacts odor concentration. And we've touched on this before, and we've seen different examples of this in the modeling. But air movement, causes that advection. That's just a transport of odorous gas away from the source. And that air movement, and specifically the velocity and the turbulence caused by that movement, is the main influence on how fast an odor loses concentration. Okay, how fast it diffuses and spreads out. And again, the speed of the air and the obstacles that it encounters, that's all going to dictate the types of turbulence that it is created, and then changes in velocity and so forth. So it all matters. So let's take a look at, what this one, which is, I'm going to say it's shear dispersion. It's kind of a combination of things because there's a little bit of turbulence diffusion in there, but shear dispersion is really just where you have different velocities of airflow intermingling in different layers. And so if I have an airflow, it's going across here, and then all of a sudden I start releasing my odor, you're going to see this odor start to spread out in that airflow. And that's because not only is the airflow causing, it to spread out because it's moving a little bit slower and it's doing that shear dispersion, but it's also doing the molecular diffusion. Okay. And any obstacle downwind, anything like that will influence this, but this is just a flow. You'll see that the biggest thing that I want you to see, though, is this is a very constrained flow. Okay, so if I draw this, that's constrained. It's a narrow pathway, a narrow odor plume, and you're going to see that in the model. And the faster the wind, the more constrained and confined that odor plume becomes. Okay. So let's introduce turbulence. And same principles. We've seen this before. We know that the odor, the airflow likes to go up and over. And then once the odor starts getting released, it's going to be carried over. But we also know with turbulence, there's an eddy being formed on that backside. Okay. And that's going to pick up and pull down some of that odor molecules and then slow it down and dissipate it lower on the backside. And all that's going to be dictated by the wind speed and the size of the obstacle. But this is just a reminder, and we've seen this in prior videos, that the odor on the backside and in the areas of eddies can be very complicated and confusing for the dog. So we just need to be mindful of that. Okay. Now, porous zones. This is one we haven't talked about before, and it's very important because we live in a world full of porous zones, specifically like vegetation. Okay, and what occurs in a porous zone is that the airflow will be coming along and it hits and it slows down, and all of a sudden the amount of air that was moving along reduces. Okay, and so it's now a much slower flow and it changes. So it kind of wants to create an eddy, but because there's airflow coming through it, it doesn't. Or at least it's not as defined. It depends on the vegetation. But really, it just kind of slows everything down on this backside. And you'll actually, depending on the vegetation, have almost zero velocity on this back zone. And you've seen that. Anybody who's been out on the plains, um, areas where it's really windy, you'll see these lines of trees and vegetation. Those are called, vegetation belts, and they're specifically put in to control the wind and slow the wind down. And it's by using this principle of porous materials, trees specifically, trees and bushes, and those are actually well engineered to slow down the wind and give a protected barrier well down range of that vegetation. And that, of course, is going to influence how the odor moves. Because now, as it's going on, that odor is coming out here, and it's slowing down and it starts spreading out. So what was once that well-defined plume on the earlier animations is now this very spread out and slowed down plume of low concentration. And you're going to see that in the models. Okay. So again, porous zones such as vegetation, it slows the airflow. Concentration levels kind of get maintained and slow down and spread out a bit. And then once it's reintroduced into the airflow, it's typically much wider than what it was at the beginning. So let's take a look at just wind and terrain. This is just going to be some rugged mountainous terrain, and we're just going to look at different wind speeds. So we're not even looking at vegetation yet. Imagine this is just bare rock. What we have here is we have 3 odor sources in different locations in this terrain. So you kind of have this high ridge line back here, this low valley, and that's where source number 1 is. And then this is, we have some higher mountains here. So this is kind of down in a ravine, kind of protected by these mountains. And that's in this area. And then this one is kind of more on the upwind side. The wind's coming from the left. And this is kind of in a more exposed area with a lot more rugged terrain that it's in. And so let's just kind of see how this works with relation to 1 mile per hour. So that this is a 20-minute simulation for each wind speed. So this first is that's 1 mile per hour, and you can see that odor plume reaches well out there. Now 5 mile per hour, you can see all of a sudden there's a distinct change in how far the odor plume reaches. It's all the same concentration, that doesn't change. And then 10 miles per hour, all of a sudden that odor plume constrains even more, even in the valley region. But that valley, the area where the least amount of turbulence is occurring, is where that odor plume is the longest in that higher wind condition. Okay, so let's just take a quick look at this. This is just a still shot. So this is the extent of the odor. You can see how wide it is on both of these. Again, this is kind of on a less protected area, or a more protected area, sorry. And this is in an area that's much more rugged, much more turbulent, but it's still able to reach out there and pretty well-defined odor plumes. Then at 5 miles per hour, you see it start to pull back. This one, just that change in wind velocity and the turbulence caused by the terrain pulls that odor plume back quite a bit. This one, reduces by almost half, and this is probably down to about, 2/3 of what it was, if not more. And then at 10 miles per hour, again, this one kind of constrains. It's pretty localized in terms of that concentration level. And then same over here is that wind picks up, it starts having more and more of an influence. And this is the only one that really still has any reach to it. But if you remember, it was clear out here and pretty wide in terms at 1 mile per hour. So that's the impact of wind velocity. The faster the wind, the more it influences and reduces the odor concentration. Okay, odor's still going downwind. Don't mistake that. We're just looking at the same level of concentration at different wind speeds. So the faster the wind speed, the lower the concentration becomes. It can't maintain that level of concentration that it was at a lower velocity. So obstacles in vegetation. We're looking at 2 different models, so this will take a little bit of time. And model 1 is just a person as the odor source. We've used this before. The gas expelled is just how much a person breathes. It's about 6 liters per minute. And so the diffusion coefficient, it's basically like air. That's really all it is. And then model 2 is a little more specific. So it's an article on the ground, and that's the odor source. So one is the person is standing up, and now we have one that's on the ground, and so you're going to see the impact of vegetation and barriers there. But the gas quantity that's being released is 10 orders of magnitude less than what was released in Model 1. So that's 1 tennis ball versus 10 billion tennis balls. So if the human's breathing out 10 billion tennis balls, the article on the ground in Model 2 is only releasing 1 tennis ball. So it's a substantially reduced amount of odor. But the other thing that's changed is that the diffusion coefficient, how fast it spreads out, is 1 order of magnitude less. So that means it spreads out more slowly, and that actually helps it maintain concentration even though there's much less gas being emitted. So just to give a quick understanding of this, this is going to be the model. Don't worry, we're going to see the animation here in just a second. I just wanted to explain this. This is the same wind speed and visual limits of concentration, but this one is the person, so you can see the amount being released, and this one is the article. Okay, So you can see that there is a substantial difference in the amount of gas being released. But again, this is just percent volume. So that's just saying that, hey, the odor is here in relation to the percent volume. It's not necessarily the quantity of it in terms of mass or molecules. And this is the same thing, but it's 2 orders of magnitude more concentrated. And so this is what I'm going to use for our baseline for this one. And then the prior one, where it's a little less concentrated, I'm going to use for this one because you can see there's a big difference. And so just 2 orders of magnitude more or less concentration can result in a distinct change in the odor plume. Whereas here it's like there is no odor plume. There actually is, but not at that concentration level. It's basically right at the source. Okay, but you can also start seeing the effects of vegetation up there. So we're going to look at the first one. Okay, again, this is just a person, their breath basically being released from their entire body, just so it makes it easier for the model. And this is the model, so just to give you an idea. So this first one, this gray surface represents asphalt, so it has a roughness to it that the model is able to calculate. And we have, our odor sources, the person, and then we have an area of low grass, about 6 inches high, and then some shrubs, which have a set porosity. And then we have an area of higher grass, which is about 1 to 2 feet tall. I believe it's about 18 inches tall grass with a porosity associated with that. And then trees that have solid trunks, but then the leaves, the needles, the branches, that's all a porous zone. And so we're basically trying to capture that. So let's just take a look at what this is. So the first part of this model is 1 mile per hour. And you can see that odor plume of that baseline concentration level is reaching out. And you can start seeing the influences of the cars. And notice how the unobstructed one, it went downrange pretty quick. And even the vegetation. But you notice how the vegetation is shifted and it's spread out a little bit more. And that's what we talked about why that's doing that. Well, then when the wind picks up to 5 miles per hour, now things constrained. Remember what we showed earlier? As the wind picks up, it's harder for that odor concentration to be maintained, except if you notice the vegetation. And the reason that you're seeing odor concentration there is because the wind velocity is less because of the concentration, or not the concentration, the wind velocity is less because of the porosity of the vegetation. That's that protective nature of the vegetation in terms of wind speed. That's allowing that odor to remain more concentrated. Okay, so and so that was at the end of 10 miles per hour. So we went 1 mile per hour, 5 miles per hour, and 10 miles per hour. Now, this is the same thing, and we're just going to do some snapshots here, but we're going to look at the different concentration levels. So this is the 1 mile per hour zone, and this is our baseline. We saw this is what the video showed, and this is what the 2 orders of magnitude lower concentration. So you can see it's a more defined odor plume, and it's spread out a lot more. Okay, and that's just because it's less concentration. So again, this isn't saying that there's no odor outside of this around. It's just saying that in this area, this is what is at that concentration level. And now the 2 order of magnitude, or 100 times less concentrated. Well, you can see it's occupying a much larger area. And at 5 miles per hour, you can see a pretty big shift. And again, you see that higher concentration at baseline basically be non-existent beyond, maybe 10 meters. And now, but then you go to the lower concentration, it's still well defined, still going down range, and you can see it's quite extensive up in this area. And again, the impact of vegetation is, you can see, relative to the odor concentration. And at 10 miles per hour, again, the constraint is even more, but it's still there on these lower concentration levels. And that's just because there's a lot of odor being released. So the wind doesn't have that much of an influence. It's still going downwind, and anyone's done tracking and their dogs cut across where the decoy is or where the person is, whatever they're looking for. and it's downwind, and you do see those head snaps. I mean, that's what we're looking at here, is even though the high concentration is staying close to the source, the dog's able to pick up those lower concentration levels and work back into it. But it's a nice, well-defined plume in an unobstructed unobstructed area. But up here, you can see all this obstruction. That odor plume is expansive. So let's take a look at it at the dog zone. Okay, we've done this before. So basically, it's basically the ground level up to about a meter. We're going to do the same thing, 1 mile per hour. We're just going to take a look at it and just kind of see what would the dog be encountering in this. And the 1 mile per hour is pretty clear. The unobstructed view, it's going downwind, no big deal. And then the vegetation slows it down. But then at the 5 mile per hour, things start picking up a little bit. The plumes start changing because of the turbulence and the changes in velocities caused by the barriers. And then you notice that those plumes start pulling back, and that's kind of that dead zone next to the vegetation. And we'll see that in the velocities section in a little bit. But the trees, what you're seeing is because there's tree trunks and the main branches are above the ground, that's able to flow underneath the trees, and that's why that plume is still established. Even in 10 miles per hour, and the reason that plume is also staying well established is because the vegetation on the ground, the grass, that influences it as well. Okay, so now you're starting to get a feel for what vegetation, what barriers do, what no barriers do. So now let's take a look at the article one. Same thing, except difference is this is on the ground, and again, much lower, odor release. And let's just take a look at see what that's going to do. Again, the odor plume's nice and defined in that unobstructed area. Staying low to the ground, though, that's going to be important. It's not going to be as high. And this one, what was interesting is it wanted to rise up, it wanted to follow that laminar flow over. And this one, it worked through and finally got through the vegetation. And then at 5 miles per hour, you start seeing this flow really narrow down. And these start picking up, okay, and be carried more vertical, because again, the flow is going up and over, and we'll see that in a little bit. And the obstacles, and then at 10 miles per hour, things start getting a lot more turbulent, and you start seeing that odor pull back and staying in that area down in between the cars. But because of the vegetation and basically the wind velocity is much lower than it is down here. Okay, but you can see this is unobstructed, and so there's no turbulence, and so you still have that nice maintained but narrow odor plume. But because of the turbulence of the cars and the velocities, it's not able to stay concentrated beyond it, and that's just the turbulence diffusion there. Whereas here, you're getting a combination, not only turbulence, but shear dispersion, because the airflow is slower going through this vegetation, and so the faster airflow wants to go up and over. And that's why you're seeing these long, exaggerated odor plumes downwind of the vegetation. So again, we're going to just look at the baseline versus the 2 orders of magnitude lower concentration. And so you can see this is 1 mile per hour. This is a baseline. So again, we had to modify the original because it was so little odor. So this is the video that you saw, and this is if it was the same concentration as the person. Basically not there. And then here, it's there. At least you're seeing, again, more of an impact. It's going back to velocity, though, and we'll see that. But really, it's not going past the source. So the same concentration level as the first model, it's not leaving the source, or at least you're not seeing it. But you are seeing it over at those 2 orders of magnitude lower concentration. And then, again, at 10 miles per hour, kind of the same effect. But now you're starting to see it more impacted and down in this area, in the vegetation area. Okay. So let's take a look at the dog zone airflows and odor plumes in relation to the article. And just like before, this is from the ground up to 1 meter. And you can see at 1 mile per hour, the wind, that well-defined plume, over here, pretty understandable, pretty, decent size, nothing too extravagant. But the vegetation spreads it out because of that porous nature of it, and it slows down the airflow. But then when the wind picks up, that's when you start seeing this shift where the odor plume, particularly over in here, starts spreading out and meandering. Keep in mind this video is sped up. And so this meandering is pretty significant. And then at 10 miles per hour, you start seeing more. But notice how this other one starts really narrowing down, almost like pencil width. And the vehicles have pretty much ended any odor plume of that concentration downwind of the vehicles. Okay, but notice the vegetation. See how it's spread out here, just like we showed in that animation earlier, that it's essentially slowing that down, slowing that enough to where it's allowed to spread out. And remember, this particular odor has less, it has a lower diffusion coefficient, so it spreads out more slowly anyways. And then this one, keep in mind the trees, the wind is able to pass underneath the trees, and that's why this odor plume it's spread out because of the vegetation, the grass, but it's still a little more defined than what it is over here, and that's just because the wind is able to pass underneath the trees. So real quick, we're just going to look at some velocities. If you notice, this is just the 1 mile per hour one. The dark blues is almost zero velocity, so you can kind of see that here, and the light blue that's 1 mile per hour. And this is a 5 mile per hour. The green is kind of that's 5 miles per hour. That's where it's at. But notice that this area, and this is again the dog zone, it's almost zero. Okay, and zero down here, a little bit faster up here, zero here. And then when we get to 10 miles per hour, you see these areas of very low wind velocity relative to everything else, but particularly in the vegetation areas. And these bushes have a big impact, these pockets of almost no wind movement. And that matters because odor is going to collect in there and concentrate. And so the vegetation definitely has an impact on the velocity, and that in turn impacts the odor concentration. And this is just real quick, looking at the streamers. I just looked at the 5 and 10 mile per hour. You can see the turbulence on the backside of these vehicles, and that influence, but almost no turbulence up in this vegetation here. And again, the air is still able to pass through it. And so that allows a flow, and you see the laminar flow going up and over. But this turbulence down here in the trees, that's all caused by the tree trunks. Okay, but it's still somewhat, linear in nature compared to these more dramatic turns in terms of the particle paths. So last, we want to close out with a real world example. I'm going to use a video we took of article search by Canine Dozer. He was still in training at this time, and he's trained by Molly McKinney of McKinney Canine in Helena, Montana, and I believe he's going to South Carolina. He's a single-purpose narcotics detection dog, and he does do article search. And she warned me, it's like, hey, he's only done 2 article searches before, but he's got a great head snap, so that's why we used him. And the keys that he's looking for were tossed out into the field 3 minutes prior to the search, and there's about a 3 mile per hour wind that is going to be coming out of the right. So she lets him off leash, and he's a young dog. He's 2 years old. He's running around like an idiot and just having fun. He's like, woohoo, we're going to go play. And he doesn't realize he's working yet. And so kind of letting him do his thing. Now, Molly is downwind. She is starting on the downwind edge of this. And we're going to see it's important. So he's running around. He's thinking they're going to play, and it takes him a little bit for him to kind of get into search mode. And then he starts putting his nose down. It's like, okay, I know this game now. And, got to come back and check. And he keeps running around, and eventually he's going to get into work mode. Because believe it or not, he's a pretty good dog. He's been fun to watch. But this is only his 3rd time doing article search. But he's running around, and he's not putting his head down as much, as you may want to like him to, but watch him kind of working that, and he's well downwind of it. Keeps coming back. Molly's doing her pattern, and he's cruising along. He's putting his nose down more, chasing downwind. Now, he may be chasing Odor downwind. That's a possibility. Heading back this way, doing good. Wham. That's the head snap we were looking for. Now, I know some of you may be thinking, oh, he didn't indicate. Okay, again, Molly hasn't worked on his indication for this particular type of work. Don't fault the dog. But what we did see is he was running around well downwind, not seeing any changes of behavior necessarily. And maybe you see some. I don't. The head snap was what was substantial. Is once he caught that odor, he went right to it. So what does a model look like? And this is a very simplified model. I did two people, two sets, so basically just different distances, just to give you size relation in terms of distance of the article. And as we're running and letting it run downwind, it's keys. It's a very narrow odor plume in this wind. That's the key thing to remember. Is because the size of the source is so small and the amount of odor being emitted is so little that the odor plume is very constrained. Okay, and there's gaps in it, and that's caused by the roughness of the grass. Okay, and that's accounted for in the model. And what I wanted to see here is we're talking concentration, and so this is the baseline that we used in the earlier models, and that's a well concentrated, well-defined odor plume. But then we increase the concentration, and you start seeing gaps. And again, that's the impact of the grass. Okay, is there's a roughness associated with the grass, and it causes inconsistency in the odor plume. Okay, but then we go 10 times more concentrated. It's basically not leaving the source. Okay, so that's something to kind of keep in mind when you're doing an article search or in an open area like that. That how it's going to behave in that vegetation, and it's going to be a much more constrained pathway in an open area versus an area with lots of vegetation and bushes and such, as we saw in the prior models. Okay, so summary, this was a long one, sorry. The odor concentration, it can vary considerably based on the source and the environment. I think we're clear on that. Wind speed and turbulence, they're the main causes of odor diffusion, and thus the reduction in that concentration. The faster the wind, the narrower that odor plume, and the lower the concentration levels become downwind. And then the higher wind speeds over and around obstacles cause turbulence, and that increases diffusion, again lowering the concentration levels. Bottom line is pay attention to your dog. Okay, the dog may walk through areas of low odor concentration, may chase it downwind. My dogs do that. And so always be mindful of the wind to help redirect the dog to the source. And just being aware of how the environment may impact concentration levels will help you plan and execute your search more effectively. So upcoming lessons, I don't have a particular one on the docket right now. I have a bunch of models. The big one's coming up is going to be buried hides. Urban terrain, I have one already built for that. I think that'll probably be the next one just because it's easier to put together for everybody. And then still working on the thermal convection of air within a room caused by windows or heater, that kind of thing. And so basically, it's a non-fan environment. It's just using the heat in the room, such as a fireplace or something. And then vegetation's influence on airflows. We kind of already touched on that, but we're probably going to dive more deeply into it, specifically in different terrains. And so we may combine that with a mountainous terrain with SAR. I've been pulling in some different terrain and looking at how to do that. So that's just down the road. I'll get to it when I get to it. I hope this was helpful for everybody. If you have questions, again, this was the longest video I've done, but if you have any questions, please feel free to reach out to me and check out my dogs, all Dante only, at Rotten Bomb Dogs on Instagram. Have a great day.